Children, today we will take mechanism of SN reaction. First we will start with SN2 reaction, nucleophilic substitution bimolecular. The meaning of bimolecular when rate is dependent upon the concentration of alkyl halide as well as nucleophile. Transition state is also appear in this reaction. The transition state is the state in which new bond is in forming state whereas old bond in breaking state. For example, when methyl chloride reacts with aqueous KOH, it results methanol along with potassium chloride. In the mechanism of the reaction, as you can see, the reacting molecule or substrate, that is methyl chloride. Substrate, it is the receptor in any reaction. This substrate molecule, as you can see, it has been drawn in three-dimensional structure. In this three-dimensional structure, as you can see from the moving cursor, two bonds are drawn by plain line, straight lines. These straight lines represent that these bonds are on the plane, whereas dark wedge is representing the bond that is above the plane, coming out of the paper, whereas shaded wedge representing the bond which is away from the plane or below the plane. In this molecule, methyl chloride, this carbon atom, it is the receptor site. On this carbon atom, nucleophile or OH minus will attack and CO bond will start forming. As you can see from this transition state, this is the transition state is formed that we have drawn in square bracket. In this transition state, new bond that is in between carbon and oxygen atom, that is in forming state shown by dotted line, and old bond between carbon and halogen atom, that is in breaking state. As this oxygen atom of the nucleophile will approach towards this receptor or carbon atom of alkyl halide, these hydrogen atom that are bonded attached to this carbon atom or receptor site, they will start moving apart from nucleophile so that nucleophilic approach to this carbon atom will be feasible and ultimately they will become planar as shown in this state. This state in which this older bond will become weaker as this nucleophilic approach will become more faster and the bond will become more strong, and the state come where this old bond or departing nucleophilic bond will break completely and a strong bond is formed between carbon and halogen atom. And as you can see, the configuration is inverted. It will be inverted like an umbrella. As strong wind will caught this umbrella, it will move in inverted form. As you can see from the diagram also, this is your OH minus, that is nucleophile. Simple dots are representing in circle hydrogen atom and dark dots are representing oxygen atom. Similarly, methyl chloride is also represented in this diagram. Transition state is formed. Transition state is no stable intermediate because we cannot separate this transition state from the reaction mixture. There is no physical existence of the states that can be separated, and this transition state formation followed by attack of nucleophile to the substrate, followed by breaking of old bond and formation of new bond, and the product formed, that is inversion in configuration. This product formed, that is totally in opposite direction from the older bond or the nucleophile that are departing. The OH bond or the new bond is formed in opposite direction of the departing bond. That is said to be inverted product or inversion in configuration. In transition state, as you can see, the carbon atom is pentavalent. It is directly bonded to 5 atoms, as you can see from the moving cursor. So it is highly unstable and immediately convert to the product with inversion in configuration. Now we will learn reactivity of 1 degree, 2 degree, 3 degree halide towards SN2 reaction. As you can see, when this coming nucleophile will attack to the substrate, these 3 hydrogen atom attached to the substrate atom will come to the planar state and they will move apart from this coming nucleophile, so that the approach of the coming nucleophile will become feasible. So we can conclude, as these group attached to the substrate atom or carbon atom, if these group are bulky or bigger, these group will hinder the approach of the nucleophile. This is methyl halide, that is CH3X. Second one is ethyl halide. One methyl group is attached to the substrate atom. Next, that is isopropyl halide. 2 methyl group are attached to the substrate atom. And next is tertiary butyl halide. 3 methyl group are attached to the substrate atom. So from 1 degree to 2 degree halide to 3 degree halide, as we move, steric hindrance increases by 1 methyl group, 2 methyl group and 3 methyl group. So nucleophilic approach will be hindered. So in terms of reactivity, we can say the rate is 30 in case of methyl halide, and for 1 degree, 2 degree and 3 degree halide, this rate will decreases, and even for 3 degree halide, it is not reactive for SN2 reaction. Now we will take mechanism of SN1 reaction, nucleophilic substitution reaction, unimolecular, when rate of reaction is proportional to only concentration of alkyl halide. Rate depends upon concentration of alkyl halide. Reaction proceed in 2 steps, that is slow step where the stable reaction intermediate is formed, and the second step is fast step where the product is formed. Reaction will take place in presence of protic solvent like ethanol, water, acetic acid. The role of this protic solvent is to break carbon halogen bond so that carbonium ion or reaction intermediate can be formed. Carbonium ion is formed as reaction intermediate, and the stability, as we know, the stability of carbonium ion is 3, 2, 1, and minimum stability is of methyl carbonium ion. If we take the example, that is tertiary butyl bromide, when reacts with aqueous KOH solution, the product formed is tertiary butyl alcohol along with potassium bromide. When we take the mechanism of this reaction, tertiary butyl bromide in step first in presence of polar solvent this CBr bond will break in presence of this polar solvent. The step is reversible. It is slow step of the reaction, and the product formed is tertiary butyl carbonium ion along with bromide ion. This is 3-degree carbonium ion, as the positive charge carrying carbon atom is directly bonded to 3 carbon atom. This stable reaction intermediate further will be attacked by the nucleophile, and in fast step the product formed is tertiary butyl alcohol. The state of hybridization in carbonium ion is sp2, or the molecule in sp2 hybridization is planar, trigonal planar. Geometry is, if we draw the structure in 3-dimensional form, then these two planar bond that is drawn by a straight line CH3 and Br, dark wedge, one methyl group is attached, and shaded wedge, one methyl group is attached. In slow step, in presence of protic solvent, the step is reversible. This 3-degree carbonium ion is formed. Further, in fast step of the reaction will result tertiary butyl alcohol as the product. Now we will learn reactivity of 1 degree, 2 degree, 3 degree halide towards SN1 reaction. First we will take methyl halide. In presence of protic solvent, in slow step it will generate methyl carbonium ion as intermediate. Next is ethyl halide. It is 1 degree halide, as halogenated carbon atom is directly bonded to only one carbon. In presence of protic solvent, in slow step it will generate ethyl carbonium ion, that is 1 degree carbonium ion. Next we will take isopropyl halide. It is 2 degree halide, halogenated carbon atom directly bonded to 2 carbon. It will generate 2 degree or isopropyl carbonium ion. Similarly, tertiary butyl halide, that is 3 degree halide, in slow step of the reaction in presence of protic solvent, it will generate tertiary butyl carbonium ion, that is 3 degree carbonium ion. As we know, the stability of carbonium ion is 3, 2, 1 and methyl carbonium ion. So, in this data, this stability of methyl to ethyl to isopropyl and tertiary butyl carbonium ion, stability increases. So, nucleophilic attack is more feasible because more stable carbonium ion will available in the reaction mixture for longer time for nucleophilic attack. So, reactivity towards SN1 reaction increases. So, in this way, we can conclude that reactivity of alkyl halide towards SN1 reaction is 3 to 1. 3 degree halide is maximum reactive. And for SN2 reaction, it is opposite, that is 1 degree, 2 degree and 3 degree halide. 1 degree is maximum reactive and 3 degree halide is minimum reactive. Children, always remember that larger is the size of the departing group, more feasibility for the SN reaction. So for halogen, this one will be the reactivity towards halide, that is I maximum, then Br and minimum towards Cl. Next we will discuss some important questions. First is, allyl halide is more reactive towards SN reaction as compared to vinyl halide. Give reason. We will take these two halide, that is when halogenated carbon atom is in conjugation with pi bond. This is your allyl halide. We have discussed in classification of halogen. This is allyl halide. When this halogen atom is removed from this allyl halide, allylic carbon atom, then it results allyl carbonium ion, because halogen will be departed in form of nucleophile, that is X minus. This allyl carbonium ion. Conjugation is there. This is your functional group carbon atom, then single bond and then double bond. Conjugation is there. So this positively charged carbon atom will ask for the electron to the pi bond. Due to electromeric effect, pi bonded electron will move from CH2 to CH carbon atom. Now the electron density from the central carbon atom will move by forming pi bond towards positively charged carbon atom, and it results next resonating structure. In these two resonating structure, position of atoms is not changed, but only charge and pi bond are delocalized, and this is the resonance hybrid. We can conclude that allyl carbonium ion will show resonance stability, as it is stable due to resonance, so available in the reaction mixture for longer time, so nucleophilic attack is more feasible. Whereas when we will take the example of vinyl halide, that is CH2 double bond CHX, when we will remove this X in form of X minus, then the product formed is vinyl carbonium ion, that is CH2 double bond CH. Two functional group, that is positive charge as well as pi bond, both are present on the same carbon atom, so no resonance stability is there, so least stable, so least reactive for SN reaction. Similarly, we will take the second example, that is benzyl chloride or phenyl chloride. Which one is more reactive towards SN reaction and why? Again, we will take the example by forming their resonating structures, that is benzyl chloride C6H5CH2Cl. When we will remove this halogen atom, it will generate benzyl carbonium ion. This benzyl carbonium ion will show resonance stability. This functional group carbon atom, then single bond and then double bond. Conjugation is there. So due to electromeric effect, position of the pi bond will shift from 1 to 2. Charge density will move towards position number 2, and then position number 2 to 3. Negative charge will move by forming pi bond, and we will get the first resonating structure. Now to this positively charged carbon atom, it is in conjugation with the other pi bond of the benzene ring. Second resonating structure will formed. Similarly, this positive charge is in conjugation with the third pi bond of the benzene ring. Again, resonance is possible, delocalization of charge and pi electron cloud is possible, and we will get the next resonating structure. Due to this resonance stability in benzyl carbonium ion, it is available in the reaction mixture for longer time, so nucleophilic attack is more feasible. That's why benzyl chloride is more reactive towards SN reaction as compared to phenyl chloride. In phenyl chloride, if we remove this halogen atom, then we will get this phenyl carbonium ion, two functional group, that is positive charge as well as pi bond on the same carbon atom, so no resonance stability, no resonance, no delocalization is possible. That's why it is less reactive towards SN reaction.